Hello everyone, my name is Mukesh, Verma, Assistant Professor at Department of Chemistry, Maharaja Agha University, and the topic of today's presentation is nucleophilic addition to the carbonyl groups. Nucleophilic addition to carbonyl groups are the most simplest reactions in organic chemistry. Addition of the carbonyl groups generally consists of two mechanistic steps. First is the nucleophilic attack on the carbonyl group, that is representing the first step. And second is the protonation of the anion, that is takes in the second step. Then to nucleophilic addition to the carbonyl groups is two steps. First is the nucleophilic attack, and second is the protonation. We can see the orbitals to understand the reactivity of the carbonyl groups. The carbonyl groups, as represented by a simple example of formaldehyde, is a planar structure with carbon and oxygen atom both are sp2 hybridized. Two orbitals are used from sigma bond with the hydrogen atoms, and one is used from sigma bond with the oxygen atom. One unhybridized orbital is used from the pi bond with the oxygen. Similarly, the oxygen, one sigma bond is formed with carbon, and two orbitals are used to contain the electrons, and one unhybridized orbital is used from the pi bond with carbon. This makes the carbonyl group planar in nature with angle is 120 degree. Why does nucleophile attack to the carbon atom of the carbon atom? And the reason for the attack of the nucleophile to the carbon atom is that there is a less electron density on the carbon atom. Due to the presence of oxygen atom, which is electronegative in nature, oxygen will draw the electron towards itself. That creates a deficiency of electron at the carbon atom, which make the nucleophiles attack possible at the carbon atom. Secondly, in anti-bonding pi-star orbital, there is more contribution of the carbon atom. This is the second reason for the attack of the nucleophile at the carbon atom. The reactivity of the carbonyl groups toward the nucleophilic attack is simply represented by these reactions. Firstly, the LUMO, that is lowest unoccupied molecular orbital, that is pi-star orbital of the carbonyl groups. The carbon atom is attacked by the nucleophiles. Nucleophile is electron rich in species, therefore they have electron in highest occupied molecular orbital. Nucleophile containing the homo electrons. The homo occupied nucleophile attack the LUMO of the carbonyl carbon to form a sigma bond, new sigma bond. When there is a formation of the bond between the nucleophile and carbon, there is a breakage of bond between the carbon and oxygen. These electrons are shipped on the oxygen, that increase the electron density on the oxygen atom. Next is the angle of nucleophilic attack on the aldehyde and carbon, aldehydes and ketones. The nucleophile cannot attack at any angle on the carbonyl carbon. The angle is fixed, that is 107. The nucleophiles attack to the carbonyl carbon at the angle of 107, which is called the Baddi trajectory. And the reason for the attack at 107 degree angle is that there is a compromise between the maximum orbital overlap of the HOMO with the pi star and the minimum repulsion of the HOMO by the electron density in the carbonyl pi carbon. As can be seen in the figure, there is a maximum overlap between the nucleophile orbital and the pi star orbital of the carbonyl carbon. When there is a maximum overlap, on the counter side there is a repulsion from the inner orbital of the carbonyl carbon towards the nucleophile. Both factors are simultaneously takes place that shift the nucleophile to attack at the angle of 107. And actually, the reason is that one reason is that the orbitals are also shift away from the perpendicular position due to the presence of node in the carbonyl carbon. The first example of the nucleophilic attack to the carbonyl carbon is the attack of the cyanides on the aldehyde and ketones. As can be seen from the reaction, in this reaction, the aldehydes are attacked by the sodium cyanide in the presence of water and HCl to form the product, that is hydrocyanide, cyanohydrogen. In the mechanism, the first is CN negative attack on the carbonyl carbon that shifts the electron density towards the oxygen atom to create the O negative ions. Then there is a protonation takes place to form the final product, that is a cyanohydrine. The attack of the nucleophile can be seen in this figure, where the CN negative attack on the LUMO or the LUMO pi star of the carbonyl carbon. The orbitals of the CN negative is represented in this figure, where the carbon atom has the negative charge and it is able to attack on the carbon of the carbon. A cyanohydride formation is reversible in nature. When the reaction takes place between the aldehyde and a cyanide, the reaction is reversible in nature. Simply by just dissolving the cyanide in water can give back the aldehydes and ketones. The cyanohydrine formation is in equilibrium. The equilibrium is more favorable for the aldehydic cyanohydrines as compared to ketonic cyanohydrines. Now, the reason for that is the size of the groups attached to the carbonyl carbon. When the hydrogen atom, in case of aldehydes, there is attachment of hydrogen atom, which is less critically limited. In case of ketones, there is a large bulky alkyl groups. When the carbonyl carbon atom changes from sp2 hybridized to sp3, when the nucleophile attack on the carbonyl carbon, the hybridization changes from sp2 to sp3, and the bond angle changes from 120 to 109 degrees. There is a decrease in angle. When the angle decreases from 120 to 109 degrees, then the group attached to the carbonyl carbon come closer. When these are bulky groups, when the alkyl groups attached are bulky, then there is a repulsion, as in case of ketones. That make the ketones less favorable as compared to aldehydes. And this repulsion between alkyl groups is called the steric hindrance. And next is the some practical example, some important intermediates where the cyanohydrines are used. Just for example, in formation of 5-HT3 agnostic, which reduce the iodine in chemotherapy patients. This is the reaction, simple reaction. There is a reaction with sodium cyanide and water. Simple cyanohydrine form. And after other reagents, the final product is formed. These cyanohydrines are also the compound that helps in the formation of the insecticide cypermethrin. In simple reaction, this is the starting reactant, and the reaction takes place with sodium cyanide to form the cyanide. It represents that cyanohydrine is an important intermediate between the most of the reactions. Cyanohydrines are also a more parts of Africa. Step food is cassava. Cassava is a food which contains the glycosides of acetone cyanohydrine. These are the glycosides of acetone cyanohydrine. The glucoside is not poisonous in nature. Glucoside is not poisonous in nature, but enzyme in the human gut break the breakdown and release of HCN takes place. When the human beings eat this cassava, the enzymes present in the human body release the cyanohydrine. And after cyanohydrine, there is a release of HCN. About 50 mg HCN is produced from 100 gram of cassava, which is enough to kill the human beings. If the cassava is crushed and washed with water and allowed to stand, the enzyme in the cassava will do the same job, and then HCN can be washed out before the cassava is cooked and eaten. Therefore, cassava is washed after its before its cooking. The cassava is not safe. Cassava is now safe to eat, but it still contains some glycosides. Some disease found in eastern Nigeria due to the presence of HCN, excess of HCN. These types of HCNs are also present in the apple pips and the fruits such as peas and apricot stones. Attack of the hydrides on the aldehyde ketones. These are second example, the attack of hydrides. Hydrides are the species hydrogen atoms which contain negative charge. A simple example is sodium hydride. In sodium hydride, sodium Na is positive and hydrogen is negative. Then H negative is called the hydride. But sodium cyanide, where H negative acts as a base, and it cannot be act as a source of hydride attack on aldehyde ketones because it H negative acts as a base and is more favorable to attack on the 1s star that is 1s star orbital of hydrogen atom to form the H2 molecule as compared to its attack on the carbon atom. Therefore, special hydride reagents are used to attack on the carbonyls like sodium borohydride and lithium borohydride. As shown in the given reactions, the hydrogen of the sodium borohydride attack on the carbonyl carbon to generate the anions. In the second step, the anion once again, the O atom once again attack on the boron atom to extend the reaction. After 2-3 steps, the final product is reacted with water to give the final product, that is alcohol. These are some examples of the attack of hydrides on aldehyde ketones. First is there is the attack of sodium borohydride and water to the alcohols. This is the second example to convert the carbonyl to the alcohols. This is also called reduction. Sodium borohydride is also a reducing agent which convert the carbonyl level 1 towards alcohols. Attack of hydrides on the aldehyde ketones. Some more examples are given. Sodium borohydride is a weak hydride donor. It only reacts with aldehyde ketones, and mostly it reacts with aldehydes and less with ketones. In the given example, there is a other functional group that is nitro, but the sodium borohydride reduce only the aldehyde. Only aldehyde group is reduced, and nitro group is present as it is. In the similar second example, the sodium borohydride cannot affect the carbon bromide bond. It only specific for the reduction of the C double bond to form the aldehyde. In the next example, example third, there is ester group, but because sodium borohydride is weak, it reduces only the specific group, that is aldehyde. Third example is the addition of the organometallic reagents to add aldehydes and ketones. Organometallic compounds are those compounds which contain carbon and metal directly. For example, lithium, methyl lithium, alkyl lithiums. For example, a grignard reagent in this magnesium carbon bond takes place. The organometallic compounds, for example, methyl lithium. The bond in the organolithium and organomagnesium regions are highly polarized due to the electronegativity difference. The electronegativity of oxygen is greater, and the metals are electropositive. Electropositive magnesium and other metals donate their electrons toward carbon, which make the carbon atom more electron rich and able to act as a nucleophile. We are powerful nucleophile because of the polarizability of the bond, and they attack on the carbonyl groups to form alcohols and formation of a new carbon-carbon bond. As we can see in this figure, when carbon and lithium bond, there is more electron density on the carbon side. Means that carbon is electron rich and lithium is electron deficient. The electron rich carbon then attack on the carbonyl side to generate the oxygen negative charge, which react with the water to form the required alcohol. But the main thing is this: there is a the reagent takes place in 2 steps. First is methyl lithium in DHF. Second step is the H2. This is very important. Notice that methyl lithium and H2 are represented in 2 steps, 1 and 2. The water second step, it means that water is added in a separate step only when the methyl lithium is completely reacted. It is because the water destroys the organometallic compounds to produce the alkanes. Because methyl lithium and methyl is electron rich, it acts as a base and react with water to form the alkanes and OH electrons. Organolithiums are used at low temperature, that is approximately minus 78 degrees Celsius, in the aprotic solvents like diethyl. because protic solvents reduce it towards alkanes. Organolithium also react with oxygen. Therefore, when the reaction takes place, these types of reaction takes place, then there is a presence of inert atmosphere of nitrogen and oxygen. In this case, this is phenylethium in the first step. When phenylethium completely reacted, then second step with the addition of water. In the second reaction, similar reaction, in this case, N-butyl lithium is used, where butyl is negatively charged, lithium is positively charged, partially negative. And negatively charged butyl attack on the carbon from the tertiary elements. One important thing is that aldehyde from the secondary alcohols and ketones from the tertiary. These are other examples. This is RMGs, where the famous it is Grignard region. The Grignard region is discovered by Victor Grignard, for which he is awarded with Nobel Prize in 1912. The Grignard region, similar case, the magnesium that is electropositive, donates electron toward phenyl, which becomes electron rich, and electron rich phenyl attack on the carbonyl carbon, which is electron deficient. To form the mechanism, you can see the mechanism in the back step. The phenyl attack on the carbonyl carbon to generate the oxygen, and ion which react with water in the second step to form the alcohols. Next is that is the fourth example, that is bisulfite addition compounds. Bisulfite compounds are made by the mixing of aldehyde ketones with saturated sodium bisulfites in ice baths, checking and crystallization. The bisulfite addition compound can be hydrolyzed back to the aldehydes in dilute aqueous acid and base. It means that the reaction of addition of bisulfite is also in equilibrium. They are usually crystalline and also can be used in purification of liquid aldehydes by recrystallization. We can see the reaction in this case. We have ketone and there is an attack of the bisulfite. Sulfur, the electron pair attack on the carbonyl carbon to form this type of intermediate. Then there is a proton transfer from oxygen to oxygen to form the bismuth addition product. And in second reaction, we can easily see that there is equilibrium, and it can easily converted by a dilute acid or base to the corresponding aldehyde ketones. But these are very important reactions. The reversibility of the reaction makes the bisulfite compound useful intermediate in the synthesis of some other aldehyde ketones. In this reaction, we can see that first is sodium bisulfite is used, and then in second step, sodium cyanide is used, but from the cyanohydrin. So why we can use this step? We directly get ketone with sodium cyanide to form the dissolved product. But if we focus on these reactions, we can see that in the first step, there is a simple addition of bisulfite. In the second step, see a negative attack on the ketone. But in next step, we can see that the hydrogen atom which is transferred by the HCl in case of addition of sodium cyanide. In this case, the hydrogen is provided by, that the proton is provided by bisulfite. When the proton is provided by bisulfite, then we don't require the HCl, and there is a less chances to create HCl, which is toxic in nature. And this is other example. The bisulfite compounds are useful because they are soluble in water. Very important thing, bisulfite compounds are soluble in water. There is a medicine that is Dapsone, which is anti-leprosy drug, and which is insoluble in water. But it is insoluble in water, then it cannot act in the human body properly because it is insoluble in body fluids. By converting this Dapsone into the bisulfite adduct, we can see that the Dapsone is converted to bisulfite adduct. This bisulfite adduct is water soluble and enter in the body very easily. Next is the addition of water to aldehyde ketones. Like previous example, the water is similarly added to the aldehyde ketones as Cm negative add. But once again, this reaction is reversible in nature, and the formation of the product after the addition of water depends on two steps, depends on two factors. First is steric factor, means that After the reaction, if alkyl groups are bulky, then a reactant is more favored as compared to product. It means that if you want to form the product, the alkyl groups must be less bulky. And if the aldehyde, then reaction is more favorable. You can see the table that acetone is used, like equilibrium constant is very helpful as 0.001. When one hydrogen is taken, then it is 1.0. When both the hydrogen are taken, means that steric endurance is reduced. Then it is 2 to 8. And second factor, electronic factor. In this electronic factor, if we take the electron withdrawing group on the carbon atom next to carbon atom, if we take the electron withdrawing groups, electronegative groups on the carbon atom next to carbon atom, then these groups attract the electron density towards itself and increase the partial positive charge on the carbon atom. The positively polarized carbonyl carbon, which make it more prone to attack by the water. When the electron density of the carbonyl carbon decreases by these groups, then the attack of water on this carbonyl carbon becomes more easy. We can see that in case of a green, the attack, the equilibrium constant value is 1.2 10 is for 6. The addition of water to aldehyde ketones is also favorable for 3-membered rings or 3-membered rings. In this case, there is a steric hindrance, or not steric hindrance, this is the strain. 3-membered rings are strained in nature, and when we attack by the water molecule, there is a decrease in angle 109. In normal carbonyl compound, there is angle of 120 degree, but the actual angle is 60 degree. So there is a difference between 60 degree. When it means that 60 degree difference takes place between the inner angle and outer angle. But when water is attacked, the angle is 109, which is very close to 60. The difference is 49 degree. So addition of carbonyl groups allows some relaxation in the strain in the small rings. It means simple means that when the hydration takes place, then there is a decrease in strain in the 3-membered rings, which favor the hydration of the organic matter. That is these 3-membered rings. Next is the addition of alcohols to aldehyde ketones. Alcohols react similarly as the water react. First step is the attack of the alcohols towards oxygen toward the carbonyl carbon, and there is a transfer of proton from the alcoholic part to O negative to form the hemiacetals. Hemiacetals are the compound in which one portion is hydroxy, ethyl oxide, and second is the hydroxy. When one hydroxy OH group is present, then it is called hemiacetal. When no only ethyl groups are present, then it is called acetal. These are very good functional groups in organic chemistry. Here are some examples of the addition of alcohol to aldehyde ketones. In the first, there is intermolecular reaction takes place, the attack of the aldehydes. Intermolecular attack of the oxygen in the aldehyde position to form a cyclic structure, and the final product is hemiacetal. Hemiacetal means that one OH is present and one is ether. When one ether is, then it is hemiacetal. When two ethers are, then it is acetal. In the second reaction, there is also the intramolecular reaction, the attack of oxide and the OH negative OH group toward the carbonyl carbon. From the one OH and one ether, means it is hemiacetal. These are some other examples. The addition of alcohols to aldehyde ketones. In case of glucose, it is also hemiacetal form. In case of ribose, it is also hemiacetal. Hemiacetal means that one is ether group and one is OH. When both ether groups are present, then it is acetal. Thank you very much.